start recording. Let's put a timer on for 50 minutes. And what we're going to do is we're going to talk about Kirchhoff's laws, sometimes called Kirchhoff's laws. I think the correct pronunciation is Kirchhoff. And 55. And this is a mathematical formalism. Sorry. This is a mathematical formalism that enables us to do complicated circuits. Complicated circuits meaning circuits with more than one power supply. When there's more than one power supply, it's hard to know which is the positive current flow, which is the negative current flow. You don't know which way the currents flow. And they fight each other or they add to each other, and you don't really know. So you need this way of systematically working through it. And Kirchhoff came up with these two rules for working through it. One of them was the so-called junction rule, where it says all the current into the junction must equal all the current out of the junction, like cars going to an intersection. You can't have cars disappearing, and you can't have cars been invented. So current in equals current out. And then the other thing we had is that when you go around a loop, then the created voltage must equal the voltage that's, I don't want to say consumed, but the voltage that's applied. So your battery creates 12 volts. You must apply that 12 volts across the individual components. You can't have voltage not applied, and you can't have extra voltage applied. So the EMF must equal the PD. Problem is the signs of it. It's like, how does it work out? Those are your two rules, basically. There's a couple of sign conventions for the loop, for the junction rule, and the best way I can describe it is I can show you it. So basically, for a junction rule, no, I want to go back one. So if the loop exits the voltage source through the positive terminal, the EMF is positive, and if the loop exits the voltage source through a negative terminal, then the EMF is negative. What is this loop? It is an imaginary circulation. It's your finger moving around the loop of wire. And you give it a sense. You either say, I'm going to go around in a clockwise direction, or I'm going to go around in a counterclockwise direction. It's the analogous to the right-hand end of the line is positive and the left-hand end of the line is negative. Who said that? We just decided. It's the same thing with this. You've got to have a way of distinguishing right from left. You've got to have the way of distinguishing clockwise from counterclockwise. So you've got to pick a direction. Yes?
So you just get to choose?
You get to choose. That's what people find really uncomfortable is you get to choose. As long as you live with your choice, then, that's great. It's when people, either they're hesitant to choose or they choose, but they don't live with it, or they don't write down their choices, in which case I have no idea, apart from the final answer, whether they got it right or wrong. So you will get points in this for the process. And if you don't write down the process, you don't get the points. It's like, so you imagine you kind of take your finger and you take it around the loop that you're interested in, and you decide, am I going to go in a clockwise direction or anti-clockwise direction? I recommend clockwise. And basically you work your way through it, and you decide on the value of things. So is this battery a positive EMF or a negative EMF? Take your loop, and if you exit via the negative terminal, it's a negative EMF. If you exit via a positive terminal, it's a positive EMF. Now, I just flipped the sign of my EMF, and that's also, that loop decision is going to flip the signs of your potential differences. So as long as you're consistent, it all works out. So what we then say is, all right, so we did the EMF, what about the potential differences? And you take the same loop, you can't have a different loop, same loop. And now you say, is the current flow through the resistor in the same direction as my imaginary loop journey? And if they go through in the same direction through a resistor, so, what did I do my pen? So on here, let me go down here and get my pen. Oh, great, I'll go back. So basically here, I came through this and I left by the negative, so that's a negative EMF. That's the first bit. But then I'm sorry. I went the wrong way. Sorry. So here, I left by the positive, my loop. Imagine the loop going actually through the wire. I draw it in the middle just because it's easy to see. But imagine it going along the wire, like a little train going along the wire. and it goes along and it leaves via the positive, so that's a positive EMF. Okay? And then you come along here and you say, well, okay, which direction does the current flow through this resistor? It flows downwards. Which direction does the loop throw through this resistor? It flows downwards. If they're flowing in the same direction, that's going to be a negative IR. You know the magnitude of this PD equals IR, whatever I is times the R. If they are going in the same direction, that's a negative IR.
IR like
IR meaning V equals IR, so that's your potential difference.
so V is negative.
So your potential difference will be negative in that case, yeah. If I flip things, if I were to flip the direction of my loop, then this would be a negative EMF, and that would be a positive IR. If you think about it, if the sum of the EMF plus the potential difference has to equal 0 in a loop, what you make, you must spend, then I need a positive bit and a negative bit. So one of them must be negative and one of them must be positive. And we don't care which, as long as one of them is negative and one of them is positive. When you get more resistors, you gotta, you know, it's not just like you can pick. So we have this loop rule to help us. So let's do one. So, all right, I'm gonna do this. I'm gonna call this one I1. I'm going to call that one I2, and I'm going to call this one here I3. Now, I could do those in any direction. I could have them all pointing towards the junction, and as long as the equation follows that rationale, it will still work, yes.
Do all the loops that you draw in the existing diagram have to be in the same direction?
I don't believe so. But why not? I'm in the same direction. But I don't believe so. I've never done it, but I don't see mathematically why. As long as some bits are positive and some bits are negative, the things that oppose are opposite sign, I think the equation works.
Okay.
So I don't believe so. So as I say on this, you can have everything pointing towards the junction, you can have everything leaving the junction, you can have some bits pointing towards, some bits leaving. The key thing is that when you write down the junction rule, you look across at your diagram and you say, for my diagram, I1 plus I2 equals I3. Agreed for that junction?
Sure.
Everybody agrees on that? The I1's coming in, the I2's coming in, and the I3's leaving. So I1 plus I2 equals I3. The traffic down Dale Maybury plus the traffic going along Kennedy equals the traffic going down Dale Maybury. Doesn't work, does it? Yep.
If you do it.
So then I3 separate between that into I1, I2 at the bottom, right?
So Dan, let's talk a little bit about that, because you don't, with practice you don't need to draw this out, but you're right. What happens is I3 is coming down here still, yeah, and then it splits, and this is I1 and this is I2. In that direction it splits, and the traffic going along this left-hand loop goes to the right, upwards, and then to the left, upwards, and then to the right. So it's I1 there, and it's I1 there, and it's going in that direction. Yep.
What is it? What is what it make it like that? Why it doesn't change? Why is
Can
it-
water, if water comes down a pipe and it splits, then all the water that enters the pipe must leave the pipe. And there's no exits on this, so all the water flowing in that direction must continue flowing in that direction, must continue flowing in that direction, must continue flowing in that direction, must continue flowing in that direction. So it's literally like water flowing through a pipe. It's a really good analogy for this kind of stuff when you're first beginning. What would water do? You know, ask yourself, what would water do in this case? So you don't have to put all those on, because you know your diagram's going to get complicated. But so that's your first bit. Let's go to a second bit now, and for this bit, actually I'm going to change colours because I want it to stand out a little bit from my diagram. So let's go to something like a blue pen. And I'm going to kind of draw it a bit more carefully than I normally do to kind of give you the hint that don't matter where I begin and end. All that matters is I am indicating to myself that I have a clockwise going loop. By the way, there's a third loop, which is the outside of the whole thing. I can give you a third equation, but there's no need for it. Yes?
You choose that direction too.
You choose that direction. You choose your current flow direction. You choose your loop direction. You just got to live with it. Just remind ourselves, we have three our unknowns are the currents, currents, and currents, yeah? Three unknowns. So I need three equations. Yeah.
It's gonna be the same direction always on both sides?
I'm going to do it that way. You don't have to, but I would recommend you do. Okay. So then we'll look at the left-hand loop. So we're going to say left-hand loop. And what I do is I just run around this thing. So I say my loop comes along and goes up, and I leave via the positive. So that's not just 6 volts. That's a positive 6 volts. And then the loop says the sum of the voltages. So I've got to add the next voltage, and it's a potential difference. So it's an IR thing. And I know its size. It's R, which is 3 times I, which is I1. I know that. I know its size, but what sign is it? Currents flowing to the right, loops going to the right, that's a negative. And then we add on our third term, we've got a third resistor here. And I know it's an IR, it's a potential difference issue, so it's an IR, let's call it an RI, so the number comes first. That's going to be 7 times I3. And that's flowing downwards, and that's flowing downwards, that's a negative. And that equals 0. Yeah?
So this is the equation that we just saw at the beginning?
Both equations. We saw the junction rule said the sum of the currents at a junction equals 0. And the loop rule says the sum of the voltages in a loop sums to 0. Yeah, so both those equations. So next we're going to do the right-hand loop.
Wait, the junction rule is, I thought the junction rule was in and out or equal.
Yeah, the sum of the currents sum to 0. In and out. In equals out.
Oh, okay,
Yeah,
yeah.
yeah.
So you just,
Yeah.
You added the 6 to the 3 and then the 7.
So how do we know that the 6 is positive, like 6 volts?
So the rule for working out the sign on your EMF is you imagine the loop flowing, the blue arrow streaming around.
It's coming from negative, getting out from.
It's leaving via a positive terminal.
Alright.
So it's what it leaves by. Is there a logic behind that? No. It's completely arbitrary. It's like computer engineering. Why should it be that, I don't know if you have it, but I'm going to show my ignorance now. I'm going to show basic programming skills here. But why should you have in fact, I can't remember any basic programming. But if you have, why should we type in array, A-R-R-A-Y, array, parentheses, something, something, to set up matrices? It's because somebody in some room sometime decided that's the code we're going to use. The computer doesn't know what an array is, it just knows what the hexadecimal symbols are when you type in array. And then it knows what to do. Somebody made it up. That's why, from my point of view, I found computer programming without a purpose to be. I did this entire course on Fortran 4 and got nothing out of it because there was no purpose to it, because I had no need for it. And then later on, when I had a need for it, I basically retaught myself the thing. And it's just like, oh, you got to remember these. It's almost like going to Hogwarts and remembering the charms. You got to Oculus repairers, you got to remember. That's how you fix your glasses, kind of thing. So it's not. Whereas physics is, I can figure this out. I can. So aliens will have computers, but they won't have BASIC. They're going to have some other language that they're using. So these arbitrarily made up things are actually quite vexing because they require all your memory, because you've got to remember the rules. So next we have this thing, and we say, well, let's look at the right-hand loop. And so this, you tell me, there's a 9 volt in there. So what's it going to be? Oh, you don't need a V in there. I'm sorry. So it's going to be -9. You don't need the V. The V is just the units. The current stands for the amount of current, but the 9 is the amount of voltage. Yeah. So then we're adding. Now look at let's do the 7 next. It doesn't matter which order we do them in. 7's next. It's going to be 7 times I3. And now the current's going down and the loop's going up, so that's a positive. And now we are going through the 5, so we have 5I2. And that's going to the left and that's going to the right, so that's going to be a positive. Equals 0. Cool. And the rest is math. We need to find something. We've all got our own way of doing things. This is my way. I look at the top and I say I1 plus I2 equals I3. So that has everything in it. And this one has I1 and I3 in it. And this one has I2 and I3 in it. So if I get what I1 is in terms of I3 and I get what I2 is in terms of I3, I can substitute in here and find out what I3 is. That's my strategy. So this takes me across to here. And I'm going to isolate I1. So I say I1 is equal to, take that to the side, 6 minus 7 I3 over 3. I just isolated I1. And then on this guy, I'm going to turn around and say, well, let's isolate I2 now. So I2 is equal to,
Isn't that -6?
let's have a look. That's 6 I left alone, so that's positive. And I left my minus 7 I3 alone, and I moved that to the other side to make it positive. Yep. So then we have I2. Going to leave that alone. Going to move this stuff to the other side. So I'm going to say 9 minus 7 I3 over 5. Am I right on those two? Do you guys agree?
Yeah, cool.
So then let's substitute these guys back in. I1 plus I2 equals I3. I1 plus I2 equals I3 gives me that 6 over 3 minus 7 over 3 I3. That's that guy. Plus I2 plus 9 over 5 minus 7 over 5 I3 minus I3 equals 0. I did a step there. I moved the I3 to the other side. Why not? So then, now, there's two minds on this. I mean, this is now, we're at the stage of doing basically algebra with a bit of arithmetic. Some people like to leave it in terms of fractions. Other people say, I'm just going to get my calculator and figure stuff out. I don't care one way or the other, actually. So let's get our numbers together at least. Let's write them side by side. So 6 over 3. And this is going to be 9 over 5. I'll tell you what to do. Let's save ourselves a bit of grief here. Let's put the no. I wish I'd not done that. I wonder if I can easily erase it. Let's see if I can just catch the corner of that. So let's do that. And let's move our other stuff to the other side. So that goes 7 over 3. And that's going to be plus 7 over 5 plus 1 I3. Yeah? So let's have a look. Let's do it by fractional way, because anybody can do it using the calculator way. So let's do it the fractional way. So that's going to be 3 and 5 makes 15. So that would be 5 times 6 is 30 over 15. And this would be 3 9s are 27, 27 over 15. Cross multiplying, yeah. And then for this one, the base again, common denominator is 15. So that would be 35 over 15 plus 21 over 15 plus 15 over 15 I3. 15's on both sides, so we can forget about them. That leaves me 57 is equal to 35, 56, 60, 71 I3. So I3 is equal to 57 over 71, which equals, did I bring a calculator today?
0.803.
Thank you.
0.803.
So this is 0.803, and it's going to be in amps. Now, that's assuming I asked you for I3. If I asked you for, so this equals I3. If I asked you for I2, I would simply say, oh, I2 equals 9 minus 7 I3 over 5, and figure it out. So that's my methodology. I'm sure there's other ways you can solve it. Just be clear about what you do, get the right answer in the end. Okay. So when I'm grading this, I look at your diagram. If you've not specified things, I can't check your work. So if you've not drawn in what I1, I2, and I3 is with directions and names.
So I3 is the current flow through the 5 ohm resistor?
No, I2 would be.
No. Oh, I see. I'm sorry. Yeah, I didn't even look at the question. So if you want the current ohm through the 5 ohm resistor, then you've got to find I2. So you would say, oh, I2 is equal to 9 over 5 minus 7 over 5 times 0.803. And I2 would equal whatever that works out to be. 0.67. So that's my real answer. Is it possible to get a negative value? Does that make any sense, a negative current?
Yeah.
Sure, just going the other way.
That's exactly right. It is going the opposite direction to what you guessed. So if you get a negative I2, we didn't in this case, but if you get a negative I2, all it means is that in that direction, it's actually flowing in the opposite direction. You do not try and use your physics intuition to get the directions right. There's nothing wrong with having a negative value. This is a kind of self-regulating thing. I was telling you something before my lack of completion came up. Yes, so we basically just, fellas, please. We basically just sort out. So when I'm grading, I look at your diagram. If there's no indication of your names for your currents or the direction of your currents, I can't do anything. I mean, it's like it's not set up. It's basically, So that's bad. Okay? You must put down the direction of your current flows and the loops. You've got to tell me that. And then once I've done that, I look across and I say, does that equation match that diagram? And if the equation matches that diagram, you get credit for that. And the next thing I look at is, does this loop rule, does the left-hand loop match your diagram? And if it does, you get credit for that. And if the right-hand loop is also matching, you get credit for that. And then there's credit for the sums at the end. So it is a question where I'm looking at, do you know how to do Kirchhoff's laws? It's not, do you know how to get the right answer? Because you could be using sort of Thevenin's theorem or some other wacky thing that is not part of the course to solve it. You could guess. That's not testing whether you know Kirchhoff's laws. So I need you to show me the work. Okay, really important in this one. Cool. And more people will get points on this than they would on the simple circuits most semesters. Because it's formulaic. It's just like people are conscientious. If you tell them to learn something, they'll learn something. Because they're conscientious. When they have a task like doing simple circuits, unless they start practicing early, they're not going to be able to do it the night before. It's just too complicated. It's like, you don't practiced dancing the night before. My daughter's doing kind of like, she's doing a camp that involves dancing, and she's like, she hates it. But you know, you don't practice to dance the night before. Your body is not trained. You don't learn to bat or pitch the night before you play for the major leagues. You train yourself. And the same goes for this. You got a simple circuits. You really need to jump on it and train yourself. Okay, bit of a line here. The reason why we talk Kirchhoff's laws as Kirchhoff's laws is because we want to use it in this next little bit. We're going to go back and look at capacitors in a bit more realistic way. We're going to look at how they charge up and how they discharge, not the fact that they can charge up and when they're charged up they have this potential difference, and they can discharge, and when they're discharged they have no potential difference. We're going to look at how they operate, not what they do in the end. And realistically, circuits have resistors in, so we should really include a resistor in our circuits, even when it's just in principle the capacitor, although we cheat on that. If I look at Kirchhoff's laws, then I've got to have another system. It's still the sum of the currents equals 0 at a junction, and it's still the sum of the EMF and PDs around a loop equals 0. But the question is, how do we get the sign for a capacitor? And the rule is, if we leave a voltage source on a positive, that's a positive EMF, because my loop, the way I've drawn it, is leaving via the positive. But what about this guy? Well, what we can do here is, we say, well, if that's a positive EMF, that's the positive terminal, that's a positively charged plate, and that's a negatively charged plate. And we say, if the loop exits the capacitor through a negative terminal, the potential difference across the capacitor is negative. So, it's the same rule, really, isn't it? If you leave a battery via the negative terminal, it's a negative EMF. If you leave a capacitor via the negative terminal, it's a negative potential difference. Yeah. So, we left via the positive in this case, we left via the negative in that case, you add them together, you get 0. So it kind of works, it's kind of nice. And why do we need that? Because we're going to kind of like wave at that as we do some math. Okay? Because we're going to say Kirchhoff's apply to RC circuits. Not Roman Catholic. I was raised Roman Catholic, so when I see RC, it immediately means Roman Catholic to me. I'm going, what's that doing there? You know, it's like, it's ingrained. They get you when you're young, and all the stuff is there. Not the. We have this R meaning resistor and C meaning capacitor, and later on we're going to do LRC circuits, and LRC circuits are inductor resistor capacitor circuits. But for the moment we're going to do RC. Okay, let's apply Kirchhoff's loop rule to this. So we have our EMF. Curly E means the voltage of your battery. So curly E is EMF. And we have my voltage across my capacitor is, well, remember that charge equals delta V times the capacitance. So then my delta V equals Q over C. So whereas in my resistor circuit I was saying, well, that potential difference is given by IR. Now I'm going to say, well, that potential difference is given by Q over C. So there's my Q over C bit down here. And it's a negative Q over C, because if that's a negative terminal, that's a negative terminal. And then I have my IR bit, and let's look at my current. I didn't actually show my current, shame on me, but that's my I. So my current comes around, so my current is flowing down, and my loop is flowing down, so that's a negative IR. So we get this little equation. Oh, I did, yeah. Good. So then I say, well, okay, let's rearrange this. So my EMF is equal to Q over C plus IR. And what this is really saying is that my EMF is equal to my potential difference across my capacitor plus my potential difference across my resistor. And we knew that from simple circuits. Yeah, EMF is spent in the circuit. These are in series with each other. So the voltage drop across the top plus the voltage drop across the bottom equals my EMF. Yeah? Okay, so now we have three possibilities. Let's take the instant that the switch is closed. So there's this battery just trying to push charge, but it can't push charge because there's a dead end at this switch. It's called an open switch. And so nothing's flowing. And then what you do is you close this switch, and typically the way you show that is you do that. So you close that switch, so now there's a circuit. And so the charge flows. And I can ask you questions about what happens immediately, what happens in a long, long time, and what happens in between. And the immediate and the long, long time, we kind of already know. This thing is not charged. Nothing is charged apart from your battery pack has voltage in it. So initially, you have no charge on the capacitor. If I have no charge on the capacitor, then Q over C equals 0. So there's no potential difference across the capacitor. Yeah? Initially, a huge current flows. And that means big current times R gives me a big potential difference. So what I get is that my EMF, which is equal to the voltage across the capacitor plus the voltage across the resistor, is basically equal to the voltage across the resistor. All the voltage is dropped across the resistor when you first close that switch, because there's no charge on the capacitor. So you have 0 and E for your two potential differences. That's logically, it makes sense. Let's go to the other extreme. The capacitor is now fully charged. Is there any current flowing when the capacitor is fully charged? If you have a road going from the car factory to the parking lot, and the parking lot is full, and the road is full, is there any flow of cars? Absolutely none. So, okay, that means that no current flowing through my resistor means no potential difference across the resistor, because V equals IR. No I, no V. And that means my EMF is now all across the capacitor. And my EMF is equal to the charge on the capacitor over the capacitance. Yeah. So if I look over here, this would be my EMF is equal to the voltage drop across the capacitor plus the voltage across the resistor. I know that's 0, and I know this guy is equal to Q over C. So I put enough charge on the capacitor until the potential difference equals the EMF. Yeah. In between, I have a bit of current flow, so I have some voltage drop across the resistor, and I have a bit of charge on the capacitor. So I have some voltage drop across the capacitor. And that's the interesting bit, yes.
So you're trying to say in here that time is a factor.
Oh yeah.
Because the second one says at T a long time.
Yep.
How long does it take for the current to flow?
So it depends upon your capacitor, and we're going to get to that in a minute. How do we characterize what's a long time, and how do we characterize what's a medium time? But, infinitely long if you like for the minute, but, in practical terms it gets there much sooner. Yeah. So you're anticipating the next little bit. I'm going to skip one slide and go to charging up, because that's what we've been talking about. It's a more complicated equation, but I'm going to skip this charging and talk about charging. Okay, so at time t equals 0, the charge on my capacitor equals 0. And a long, long time when I'm fully charged, the charge on my capacitor still equals V times C, but it's going to be I'm sorry, this is my terminology. I wasn't familiar with it. That is my initial charge. Initial charge equals 0. And my final charge once it's fully charged, is equal to, well, remember what we said? We said C is equal to Q over delta V. So my final charge would equal, well, my delta V is E in this case, so C is equal to Q over my EMF. So my, so my EMF is basically so the charge becomes my EMF times my capacitance. That's where I end up. So let's draw that. That's my Q max, and that's my Q min. Q min 0, Q max. And it goes in between. And I think intuitively you can see when you first begin charging, there's a lot of current flowing because there's very little charge, electric field pushing back. So you get a big current, which means a big change in charge. Current is charge divided by time. So if you get a big current, you get a big change in charge in a given time. And so we get a steep slope on this. And then it gets shallower and shallower and shallower until at the end, and you can argue when does it actually truly reach its fully charged state? Infinite time, but we get close enough relatively quickly. And if I want to characterize this, so I know what's a short time, what's a long time, I have to look at this, and what they do, it comes out of the math. Well, let's talk about the math for a bit. If I look in between, my EMF is equal minus my charge by potential difference across my capacitor plus the potential difference across my resistor is equal to 0. So it's E minus Q over C minus IR equals 0. And if I recognize that I equals the amount of charge per second flowing, that I is equal to dQ by dt. So I get E minus Q over C minus dQ by dt times R equals 0. And what kind of equation is that? What classification? What would a mathematician call that equation? So what was it? Differential equation. Differential equation. So we don't do differential equations. We don't need it for this class. Which isn't required for this class. So I pull the answer out of a hat. And you either know how to derive it or you learn it, but it comes out to be this. And it's that the charge, which gives, I'm cheating like crazy, solve for Q. Charge on the capacitor, which varies in time, is equal to my EMF times my charge on my capacitor. If you think about it, that's your Q max, isn't it? Isn't that Q max?
Yes.
Modified by this factor. And the factor is 1 minus e to the minus t over RC. 1 minus e, this is a power, minus t over RC. I don't know about you, but, exponentials, I didn't pronounce them correctly for the longest time. Never mind, anymore. Play with them. Just put negative values in, put positive values in. See how they behave. Get comfortable with them. Don't regard it as being a magic equation. And basically what we do is we say, well, that equals 1 minus that. This is the time that I am interested in. So that would be t. That's the time. And this value is the q. So this equation will literally give me this graph if I plot it out. And we have this thing underneath. This time is modified by this RC value.
Tau.
And that's what we call the time constant tau. So this is tau. So if you want to know how quickly the capacitor will charge up, you can say, well, it gets to 63% of full charge in tau seconds. What's tau seconds? It's going to be R times C seconds. Let's say we have a 5 farad capacitor and a 6 ohm resistor. That would be 30 seconds. So when I'm asking you for instantaneous, it's within a split second. When I'm asking you for a long, long time, it's so that you've gone to this extreme where you're fully charged. 10 minutes, 2 days, whatever you like. in between, I want to be in my question asking around tau seconds. I don't want to go so quick that it's basically 0. I don't want it so long that it's 99%. I want to be somewhere in this range. So that's me as a question master. I will basically turn around and say, pick an R, pick a C, pick a time around the time constant. So the graphs always look the same. All that happens is that the scale changes on my time because tau occurs at a different amount of time, and my scale changes on my total charge because the maximum charge changes. But if you were to scale everything so it all fit on your page nicely, all these graphs would look identical because it's the same shape to the graph.
If it depends on time, why are we graphing in terms of tau?
No, I'm graphing in terms of time.
Oh, it's time?
It's just that I'm just giving you some information here. Tau equals RC,
All right.
and that is that time there. Yeah. Well, you got to figure it. Okay, let's go back one. The easier equation, which is basically the discharging of a capacitor. So what we do here is we basically disconnect the voltage source, so the potential on the capacitor stays the same. And then, so basically I go from this. I go from that, where now this is fully charged. And then what I do is I disconnect that. Let's just break that circuit there. And I put a piece of wire across there. Not across just the capacitor, but across the resistor as well. So I'm discharging the capacitor through the resistor. I will see that graph. It's just the opposite. It's the maximum charge modified by e to the minus t over rc. So you just got to remember that for charging it's 1 minus e to the minus t over rc, and for discharging it's e to the minus t over rc. Those are your two modifying factors. And what you're modifying the maximum charge.
So at the extreme it's vice versa, right?
Sorry?
When time is 0 and when time is too long, it's vice versa when it's charging?
Yes. When it's discharging, when time is 0, you basically got a lot of charge, so a lot of potential on your capacitor. And when you're at a long, long time, there's 0 potential because there's 0 charge on your capacitor. Set pieces, you can get one or other of those, I'll tell you that now. So learn the equation. Partly the reason why you want to learn the equation is because it's going to come up again when we do magnetism. Something similar anyway. So shall we do one? Let me make something up. Thank you, Ta. Thank you. Thank you, Ta. So, how am I doing in terms of time? Good, I've got about 11 minutes. So let's do this. So we're going to have a 8 volts, 4 ohms, 6 farads. Find for me, please, the charge at t equals 12 seconds. So how would we do it? We'd say E is equal to 8 volts. I'd say R is equal to 4 ohms. I'd say C is equal to 6 farads. I would say, oh, my Q, which is time dependent, is equal to, if you like, Q max, 1 minus e to the minus t over rc. So Q at 12 seconds is equal to E over E times C times 1 minus e to the minus t over rc. So Q at 12 seconds is equal to, what's my E? 8 volts. What's my C? 6 farads. 1 minus e to the minus t. T we said was 12 seconds over RC. RC is 4 6s 24. Oh, that's okay. Which equals 6 8s are 48. 48. 1 minus e to the minus 0.5. So the way you do this, oh, just get me a calculator. Isn't that great sometimes? So you do this, you go, you look on here and you find your exponent, which is, it's the blue color, I think. Let's look, I had it the other day. Oh yeah, second ln is your exponent. Little negative, because you can't use a negative sign, you've got to use that little negative, that's part of the numbers, 0.5, close your brackets, enter. So that's that bit. 1 minus second answer gets me that bit, times 48 gets me that bit, and I'm getting 18.89. It's going to be coulombs. And the way I check it is I go, there's my Q and there's my T. My shape looks like that. Here is my tau. And I am my tau, well, the maximum value, 6 8 is 48, that's 48. So I know that at that point I'm at 63% of it, and I'm earlier than that, I'm only halfway there. So that's kind of where I'm at. And yeah, it looks about right, isn't it? It's less than half of what it should be. Less than half of its maximum value. So I'm happy. Yep. Question or comment?
But how do we know by looking at the graph if it's charging or discharging?
Oh, I got to tell you that. That was in my words. Yeah, I got to tell you that.
So it depends on what you told us, that's the formula that we're going to use.
I'm sorry?
So it depends on what you told us.
Yeah,
That's gonna
always,
be
yeah.
the formula that we are
Yeah,
going to
if
use.
I'm telling you it's charging, you're going to use the charging formula. If I'm telling you it's discharging, you're going to use the discharging formula. Yeah.
I just want to make sure in the second line, but those are T's, right?
Oh, yeah, these are T's.
Okay, awesome. Oh, they're all T's.
Yeah.
No, that's.
Oh, RC.
The bottom is C.
That's a C.
Okay. All right, cool. I just wanted to make sure.
Yeah, good question, because, you know.
And the bottom one is a T as well.
Which bottom one?
The one in the graph?
Oh, it's a tau.
This guy?
So like that.
That's a
The
tau.
one below it.
Oh, yeah, that's it. Okay, cool.
Go. Okay, let's end it there.